if you take a spring and you grab it with your hand, you grab it with your hand and you pull on it and cause it to stretch out. Well, what happens in the spring? Springs resist stretching, so the end of the spring gets pulled back with a spring force. Notice, by the way, that when you displace it to the right, stretch it out to the right, the spring force is in the opposite direction as x, the displacement. Likewise, if you take that spring and you compress it, push it into the left, now you're taking that spring, you're displacing it to the left, and what would happen? The spring resists compression too. So there's a spring force resisting that displacement. So the spring force pushes back to the normal relaxed length. Here is that relaxed length. That's where the spring wants to be, and it pushes itself back to that length. Notice how the force and displacement are always in opposite directions. Here's the equation. We call this equation Hooke's law. And it says the spring force is negative the spring constant times the displacement. This is the stiffness, or spring constant as we call it, in units of newtons per meter. This is the displacement of the spring, how much it's stretched or compressed, measured in units of meters. And the negative sign is there, as we've already looked at, because F spring and the displacement are always in opposite directions. So let's use Hooke's law, this equation, to solve a problem. Okay, you've got a spring sitting like this on the ground. And then you place a block on top of the spring. Here's maybe it's a ball. The mass of the ball is unknown, but the spring has compressed down a distance of 34 centimeters. The spring constant we know, it's 62 newtons per meter. How can we solve this problem? Well, let's think about the forces. And by the way, the spring is compressed. This part is important, and it is in equilibrium. So we kind of allow that spring to sort of stop. You know, if you just like throw this thing, throw the ball onto the spring, it might bob up and down. The spring might bounce up and down a little bit, but we're just gonna kind of bring it to rest. It's stopped here. That's where it's at equilibrium. So what are the forces on the ball? Well, gravity pulls it down, and the spring force resists that compression, so the spring force points up. Now, we know that the spring force has to balance the gravity force. Why? Because the up force balances the down force whenever you are in equilibrium. So the spring force, we have a formula. It's negative kx. Well, but here's the thing. When we balance ups and downs, we take absolute values. So I need to be taking absolute values, and that negative sign is going to go away. And this is what we get. This equation we're going to see a lot. It only applies if we have equilibrium, and it never applies to any other scenario. Look at this, we know K, we know X, and we know G. So we can isolate and we can plug in and solve for the unknown M. K is 62 newtons per meter. X is 0.34 meters. I have to convert from centimeters. G is 9.81. And when I solve, what's this come to? 62 times 0.34 over 9.81. 2.1, we'll leave it at 2.1. The unit here is going to be kilograms.